That's that's problem solving. Thank you. Okay, I want to start with brief information about the midterm. So I just want to maybe discuss the last problem because I believe the other problems were pretty technical ones. So if you look at the last model about the model and population, this was actually the worst model because if you predict all the people as well, so just label all the peoples by class negative, so they don't have disease. Then, because the disease affects only 100% of the population, your model that predicts all people as well will have accuracy 99.99%. So it means that this dummy model results in very high accuracy. So we don't detect sick people at all. Maybe, but so because it's unbalanced data, we can't use accuracy as measure. And so the answer was or A or B, because in case of A, if we calculate the probability, it will be 2.6%, and the model performance is 6%, so it's higher than random guess. And for the second model about robotic chicken, it will, because it runs 1,000 times, so once a day it will be hit. And there is a question if it's expensive to repair this robotic chicken, because if it's expensive, maybe the first model is better. Okay. Do you have any other questions about? Yes.
So the ultimate issue with C is just the sample size being too small. Or
Not the samples, no, you can use the sample of the entire population, but the class, this class of sick people is very small. So it's unrelevant.
But it says it predicts that affliction with 99.9%. That wouldn't that also that just mean
It means that if we predict all the people as not sick people, it will be a 99.99% accuracy, because we will make an error only on the sick population, which is very small.
so basically it has to do with that if everyone we predict if it predicted accurately and everyone is sick, that doesn't necessarily mean that everyone is sick.
Wait. No, we predict that everyone is not sick. That everyone is actually good. But this small number of people, 100% of population, which is really sick, we also will predict as not sick. So we should use some metrics like recall maybe here, so get better estimation. Okay, are there any other questions? If not, we will move forward for today's topic, which is deep learning. Okay. Camera stopped working. That's okay. So I think everybody saw captures, and I want to talk about this specific capture from Microsoft. So it was proposed in 2007, and it contained 12 images of cats and dogs. And if you click correctly classify cats and dogs, then you will pass this capture. Also, it was interesting because under every picture there was a link. All these images were taken from animals from some shelters, and you could click on the link and adopt this pet. So at that time, 2007, neural networks were not popular, so people didn't use neural networks for images, and they used some classification algorithms like support vector machine or simple logistic regression. And they used features from images. For example, they try to detect the ears or whiskers, for example, on the picture. So it was all hand created features. And then they use these features as axes in your linear model or logistic regression, for example. And the accuracy was about 60%. But if you think about the solving this capture probability, you should multiply 80% 12 times. You will get about 30% accuracy. So it worked well at that time. And this, there was a competition to solve this capture automatically. So, because the accuracy was pretty low, it wasn't, it didn't hit like average, like 50% accuracy until the first powerful neural networks that were designed for images, convolutional neural networks, were proposed in 2012. We will talk about convolutional neural networks in 2 weeks and history. So the first popular architecture, AlexNet, was proposed in 2012. And then the prediction on these images became more than 90%. And if you multiply now this number 12 times, you will get higher than random guess accuracy. And in 2014, this project was closed because now everybody could solve this with neural networks. Let's look at the history a little bit of these models. So you can see here, like, what is that? 19th century linear regression, fingers, neighbors, and 20th century. Then support vector machine, k-means clustering, random forest model ensembles in the about millennium. Then the first neural networks, DGG, and then here AlexNet appeared, and yeah, it's not it's pretty recent, the gradient boosting calculation, so that we covered last week. And currently, as I mentioned before, the gradient boosting is still used for table data, but for non-table data, like non-structured data, like images, speech, what else? Texts, we use neural networks because they are more complex models and they perform better on more complex tasks. We will talk about this later. Okay. So in the late 80s, there was a paper about approximation of functions with sigmoids, You remember sigmoid is a function that goes from 0 to 1, and we use this in logistic regression. So there was a paper that claimed, and we will prove it today, that arbitrary function can be approximated as linear combination of sigmoid functions. And as you remember, for example, regression model, we have a function and we want to predict the values of this function. So it's the same as approximation task. We want our model to approximate with our model this function. So let's look at the sigmoid function. So in mathematics, it's well known. By definition, the integrable function is the function that can be approximated with this so-called indicator functions. But I will call this just step function. Step function is just the function that goes from 0 to 1, but this partially constant function also looks like a step. And in math, you know that every function, integrable function, can be approximated by these step functions and indicator functions. So if we can approximate this function with sigmoid functions, then we can approximate arbitrary integrable function with sigmoid functions. So let's try to figure out how to approximate this partially constant function with sigmoid. So if I just draw sigmoid, this orange line, you can see that it has low slope, but if you use sigmoid, for example, with some multiple, like here I'm using 5x or 5x, then the slope will be higher, and it will approximate better this step. How to approximate the second side? How to flip sigmoid or arbitrary function? If we have f of x, to flip this function, we should use f of y. No, f
Because because the one where I exposure date we actually very use the opposite
no, I mean to flip around y-axis. So, for example, this function is y equals x. What is the equation for this function? Negative. So, in general rule, if you want to flip, you should use f of negative x. And on this plot, I was using sigmoid of second, I made a misprint here. It should be 5 minus x because sigmoid of negative x will look like this, and then we should shift this by 5. And this is all the proof. We proved this theorem that every arbitrary function can be approximated as a linear combination of sigmoid functions. And this idea led to the actually, I think now it's easier to look at neural networks from this perspective. So let's say we have some input features x, x1, x2, and so on, xd. So this is our vector of features. And we have some target y, and we want to build an approximation of our target. Based on this theorem, we can use the linear combination of sigmoid functions. So let's look at sigmoid function of some weights. So because I will use also superscripts, I will use dot product. For dot product, just dot. I won't use transposition. So the dot product of the weights wx, where w1 now is a vector. So w1 will be a vector of size d plus b1. And then, as you remember in our previous example, we used sigmoid of x and sigmoid of negative x and multiplied by some constants. So that's why I'm using sigmoid of some linear combination of x's. Then we will use another sigmoid. And I leave space for weights also. And so on. Let's say we will use D1 sigmoids. And we will also take a linear combination of these sigmoid functions. So I will use another weight here, and I will use superscript now here to distinguish between these weights and biases. So I will take a linear combination of these sigmoid functions. So I want to approximate my target y. With this linear combination of sigmoid functions, where every sigmoid function is calculated from a linear combination of my features. And this is called, in this case, two-layer perceptron, or two-layer neural network. Um, plus bias. So, yeah, so this is a linear combination of sigmoids, and from the theorem that we mentioned above, it should be a good approximation for arbitrary function. So let's write this in a little bit different way, how you typically see this in the literature. So we will use the feature. And also we have data x with subscript I and y with subscript I. I just skipped this additional index of the data points, but we also have the index xi. So everywhere actually I had to use the index of my data point. So let's write down these features in circles. So this is our input to the model or to the neural network. We want to call this model as neural network. Then we calculate the cross linear combination. So let's denote this by H from hidden. It's called hidden layer. It will be called hidden layer of neural network. Okay, so the first step to calculate these hidden variables from our input. So, and just we're not limited to have the same number of hidden features. This number of sigmoids can be arbitrary, so that's why here I'm using D1 for the dimension and D for the input dimension. D1 can be different. H2 and so on. H with index D1. So every H is calculated as a dot product between some parameters W. If you want to write this explicitly, it will be W11 X1 plus W1D xd. So just the dot product with features plus bias. And we can denote this as follows. So to calculate H1, we should use all the features, x1, x2, and so on. And x1 we multiply by the number w11.
So basically,
The x2 we multiply by w12, and the last feature we multiply by w1d. So this is just the visual illustration of my formula for H1. Do you agree that this is just illustration of this H1 as the dot product between X with some vector W1 plus bias. To calculate H2, we will use also all input X's, but with some other constants, some other weights. So let's use another color. So to calculate H2, we also will use all X's, but we will multiply them by W21, W22, and W2D. And we'll add B to the bias term. So this is how we calculate these H variables. Now, what is the next step? The next step, we should apply sigmoid function to H variables. In neural networks, it's called activation. So I will denote this result by A. So then we apply to every hidden node sigmoid function, and we will denote this by A. So this is A. So the number of nodes for A, it will be exactly the same as the number of nodes for H, because we just apply sigmoid function to H. And finally, we should take a linear combination of these A variables to get the output. So output is the linear combination or dot product between weights W and vector A plus bias. So it means I will take A1 and multiply by number W11 with superscript 2. Then I will add up A2 multiplied by number W12 and so on. So I will take just a linear combination of these variables A. Okay. So if you look now at your problem solvings, you will see exactly this graph. Yes. Um, and sometimes people call these nodes neurons, but in my opinion, it just obscures the understanding of the model, because these are just numbers to which we apply linear functions, activations, sigmoid functions, and then take again linear combinations. You remember last time we were talking about blending models, so it's kind of blending of these linear regression models. And in the end, we have output, and we should compare this output with our target y and calculate the loss function. So the loss function will be 1 over n sum over from 1 to n. For example, if we use MSE loss, it will be just the square difference between output and the target. And we will minimize this loss. And now I want you to think about to minimize with respect to which parameters. Oh, yes. To minimize what we want to learn from this model, which parameters we want to tune. Yes, weights and biases and biases. Yes. So we want to minimize this. So the output will depend on all the weights from our second layer, and this A, they will depend on the weights from the previous layer. So the output actually will depend on all the parameters of our model. So we want to minimize this with respect to all parameters from the first layer. And I'm not using subscripts because I just mean all possible parameters W11, 12, 21, and so on. And actually, it's maybe better to denote this by actually matrix. Let's denote this by matrix that contains these numbers. Let's see. So if we write all the weights in the matrix, then we can just write that we minimize with respect to these parameters W1. Then we have a vector of biases. So if we denote by B1, a vector of numbers B1 and so on, BD1. And then we also can construct a matrix for second layer. It will be the same matrix, but this superscript will be 2. And the bias here. Well, in this case, I have one-dimensional output. So this vector has actually size 1, just one number, but we can have actually multi-dimensional output. Then we will have a vector for bias 2. Okay, so this is the this is our model. This is our model. So our first problem is solving how to find the parameters, take a gradient with respect to these parameters, and initialize randomly, take the gradient and update. So our first problem solving is to calculate the gradient of this loss function with respect to only 2 parameters, because next time we will actually derive formulas how to update the weights for the entire matrix instead of using just individual elements. But for today, just to give you some idea we will calculate derivatives with respect to individual parameters. Okay, and about notation, the input we don't count as a layer. So the first layer of our neural network will be H, and so this will be layer 1. And when we calculate another linear combination, it will be layer 2. So I didn't like that we will talk about multi-layer perceptron. It's two-layer perceptron. Okay, so and you can imagine that you can repeat this layer multiple times and you will get a deep neural network. Actually, two-layer neural networks is called shallow neural network. Every neural network with more than 2 layers is called deep neural network. So, okay, let's do our first problem solving. To calculate the gradient with respect to weight W12. So the weight W12 will be here. And to make our life a little bit easier, let's denote the individual difference by L with superscript I. Because we will calculate the derivative just of one square difference. And then we will just take the sum over all possible points xi. So we want to calculate the derivative of Li with respect to W12 from the second layer. What is that Li? It's the difference between OI minus yi squared, which variable depends on the weight W2, y or O. Y is a constant, it's a target. So using chain rule, we should take the derivative of the square. So it will be 2 times OI minus yi. Actually, I will write more in more details and in more detail. So partial Li with respect to O, because O depends on the weights times the derivative of O with respect to our weight. It's just a chain rule. So what is the first derivative? The first derivative will be just 2 times O minus y. So the first derivative will be 2 times O minus y without square. What is the derivative of O with respect to W12? If we write this more explicitly, it's 1 times A1 plus 1 times A2 So what is the derivative of O with respect to W12? A2. A2. And that's it. A2 times A2. Well, if you want to substitute, what is that A2? A2 is the sigmoid of H2. But I don't ask you to write this explicitly for all the x's. So we can leave this just as A2. And the final answer, the derivative of our loss function L with respect to this parameter W12 is 1 over n sum over all points I. And we can factor out 2. Oops. Okay, so this is the final answer. So now let's calculate the derivative with respect to a parameter from the first layer, a little bit deeper, with respect to B2, with respect to this number, B2. So I will copy paste this part because we will need it. B2 from the layer 1. So let's think again, only O depends on parameters. So that's why the first derivative will be the same. Derivative with respect to O, but then derivative of O with respect to B2. But let's take a look. What depends on B2? So B2 is here. B2 is here. Does A1 depend on B2? No. does A2 depend on B2? Yes. So only this A2 will depend on B2. So let's take a look at this sum. Does this term depend on B2? No, because it depends on A1. So only this term will depend on B2. So does W depend on B2 or A depends on B2? Only yes, only A. W will be like a constant. So we will calculate the derivative first with respect to A2, and then the derivative of A2 with respect to B2, again using the chain rule. But now it will be a little bit deeper. So first we'll calculate the derivative with respect to A2, because only this term depends on B2. And then multiply by the derivative of A2 with respect to B2. So this is our final expression. With respect to B2 from the first layer. So the first derivative is the same, 2 times 2 times O minus y. But the second derivative, what is the derivative of our output with respect to A2? What will be the derivative of our output with respect to A2? It will be this constant, W1. And finally, derivative of A with respect to B. A is a sigmoid function. So we should take the derivative of sigmoid function. And actually there is missing one more step. A depends on H. So first I will take derivative with respect to H, and then one more derivative of H with respect to B2. I. I have forgotten that that A is actually sigmoid function that depends on H, and H depends on B. So then what is the derivative of A? This is the derivative of sigmoid function. And we didn't talk about this, but one more reason why sigmoid function is popular, because its derivative equals to sigmoid function multiplied by 1 minus sigmoid function. Let's prove this. So it will be 1 over 1 plus e negative x. If we calculate the derivative, it will be negative 1 plus e negative x squared times negative e power negative x. And If we write this expression, sigmoid function times 1 minus sigmoid function, if we use common denominator, 1 will cancel out and we will get e in the numerator. So the derivative of a with respect to h, let's just use maybe a sigmoid prime, or you can use sigmoid times 1 minus sigmoid. So sigma prime derivative of h. But this is how to calculate this derivative. Times, and finally, what is the derivative of h? So this is h with respect to b2. What is the derivative of h2 with respect to this constant term b2? 1. Okay, so this is the final expression. And don't forget to write the sum over all I. Okay. Problem 2. Assume now that the input dimension is d and hidden size is 10. Write the dimensions of all matrices. So let's think about what is the dimension of this matrix. Its dimension is the number of rows, which is the size of our hidden layer, times the number of columns. So if our hidden size is 10, what will be the number of elements in this matrix? If input size is d and the hidden size is 10. 10 times d, it will be 10d. What will be the dimension of vector b? D or 10? 10. So it will be 10d plus 10. What will be the dimension of the matrix W2? If the output is one-dimensional. So W2 because the output is one-dimensional, it will be just one row of size, the output size times the hidden size. So how many parameters we will have in the second matrix?
This could be 10.
10. And how many parameters we will have in the biased term from output? Just one. So yeah, so sum up these numbers and this will be the final answer of the total number of parameters in your neural network. So for example, when you hear something like 7 billion parameters, this is how they calculate these parameters. The number of weights in our matrices W and the number of parameters in biased terms. Okay, what's next? So yeah, so for example, yep. For D1, for hidden dimension. So this is an example. For example, we want to approximate the absolute value function with a neural network. Then the output will be one dimension. But if it's would be a two-dimensional image, then the output could be two-dimensional. And if we use matrix notation, instead of writing these two lines like on the top of your chromosome, you can write just very simple notation. So how to get, for example, H1? You should use the first row of your matrix W1 times X1. How to get H2? You will use second row of matrix times X. And to get the entire vector H is the same as multiply your matrix W by X and plus bias vector. Then you apply activation function, sigmoid. There are many other activation functions we will talk about that later. And finally, we apply the second matrix to this vector of A's. So this is matrix representation of neural network. So the next topic that I actually prepared for today is automatic differentiation. How computers calculate the derivative automatically, because the main problem with here is to update our weights to take the derivatives, and then you update the weights as the previous weights minus learning rate times the derivative. So let's talk about the automatic differentiation. And there are different frameworks. We will use PyTorch, which has the implementation of automatic differentiation. I'm sorry if you're tired of math, but it will be interesting how computers actually calculate functions. So, and we will cover two modes, forward mode and backward mode. Forward in computational graphs. Forward mode and backward mode, and there's also a combination of these two cross mode. So let's say we have a function f of x1, x2. Don't forget to put your name on the problem. So now it's unrelated to our neural network architecture. Let's just look at arbitrary function of three variables and understand how computers can calculate the derivatives of these functions. So, for example, this function looks like this: x1, x2, sine of x3 plus exponent of x1 times x2, and everything divided by x3. And our goal is to calculate the derivatives of f with respect to x1, to x2, and to x3. And the vector of derivative is called gradient. So first, let's build so-called computational graph. How actually computer actually evaluates a function. We have three inputs, x1, x2, and x3. And then we should apply the multiplication operation between two first variables. So I will denote this variable by x4 and x4 will be multiplication of, sorry, I don't know why there are different colors. Will be multiplication of x1 and x2. And let's denote this node by multiplication. Then we should apply sine function to x3. Let's denote the result of sine of x3 by x5. x5 will be the result of applying sine to x3. Oh, I won't write x3. It will be just a function sine, which is applied to arbitrary input. Then we should multiply x4 and x5 because it's x1 times x2 is x4 times x5. And we will denote this by okay, first I apply exponent to x1, x2. I just want to keep the same notation. And then I will sum up, I will multiply x1 and sine, and I will denote this by x7. So x6 will be exponent of the product of x1 and x2. The product of x1, x2, and sine, I will denote by x7. And finally, we will sum up this x7 and x6. And we're almost there. The only thing remains to divide x8 by x3 to get the final value of our function. So this is this addition. And finally, we should divide x9, which is the same as f, is the division of x8 over x3. So this is called computational graph. And now we want to calculate the derivative of f with respect to x1, for example, which is the same as derivative of x9 with respect to x1. So x9 depends on two inputs, x8 and x3, and we know the operation, which is division. So using chain rule, we should write this that it should be the derivative of x let me see the derivative of x9 with respect to x3 times the derivative of x3 with respect to x1 plus the derivative of x9 with respect to x8 times the derivative of x8 with respect to x1. So it will be the derivative of x9 with respect to x3 times derivative of x3. Okay, I think we don't have time to cover this topic today. Let me just finish this derivative partial of x3 with respect to x1. I overestimated at the time. Plus derivative of x9 with respect to x8 times the derivative of x8 with respect to x1. I hope you agree with this formula. Then we will move to the next level and we will calculate the derivative of x8 with respect to x1. It will use derivatives of x6 and x7 with respect to x1 and so on. And we will continue next time and we will figure out how to calculate automatically derivatives. Yeah, so that's it for today. Please.
I'm guessing that the part that the parameter in this case is just really something kind of like linear regression where it determines the weight of a piece of data for the subcontext. So basically, in this case, because there's
These are the
then these and then this
this is just linear regression.
or single vectors and submatrix in the purpose layer, right?
Yeah, you can think about it just multiple linear regressions.
So basically, so in that case, there'd be 100 parameters, 100 parameters.
We don't know.
Oh.
It will be
Oh, indeed.
so. Matrix W1 is D times D1. This matrix will be D times D1.
Yeah.
No, sorry, D1 times D. So this should be D1 times D.
Yeah.
Oh, I don't have.
I can go get mine.
So, and because D1 is 10,
And then
the result should be 10D. This is correct. This is not, this is 1 by 1.
Oh.
Because
Oh,
this
yeah,
is-
yeah, it's just one, this one.
So this should be 10 and this should be 10. No, wait, 10. Yeah, this should be 1 by 10. This should be 10 by D. This should be 10, 1 by 10.
1 by 10, 10 by D.
Yes.
Oh, my.
Oh, 1 second, I will stop recording.